Okay, guys, in this lecture, we're going to be studying kinematics. And in our study of kinematics, we'll have to very deliberately discuss distance versus displacement, speed versus velocity. Both of those are scalar versus vector decisions. But we'll also discuss acceleration for the first time, final velocity and distance traveled during constant acceleration is going to be a topic. And we'll even do free fall. And I think the thing that links all of these sort of last topics together is that it's straight line motion. So there won't be any curvature of any type. There won't be any forces needed to keep these objects in motion. So straight line and forceless are the unifying themes here. There is an enormous homework assignment associated with this lesson, but of course the benefit of a flipped classroom is that we can save that homework for in-class time. So just be aware that this giant assignment will be done in class. I want you to pause the video here, read the do now, and think about what your answers would be, but don't write them down. All right, so our first discussion here is going to be a discussion of distance versus displacement. So when an object moves from one point to another, it experiences a change in position. And you could just move in a straight line and stop, and then we could measure that difference in position. We could call it distance. Or, you could go in a straight line and stop, change direction, move in a straight line, stop, change direction, move in a straight line, stop, and you could change direction as many times as you want. And you could still track each of those individual changes in position, and the total position that you moved is what we would call distance. Pause the video and think about whether you think it's scalar or vector. And as a refresher, scalar means that it doesn't have a direction associated with it because it's just a size, it's just a number. And then vector means it does have a direction associated with it because not only is it a number, it's also a direction. All right, so final answer here is that distance would be scalar because it's just a magnitude, it's a total distance, but it doesn't have a direction associated with it. Now, distance has a cousin, I guess, and the cousin of distance is displacement. So it's really, really similar because you're still measuring the change in position initially of the object versus only its final position. And the way that's similar and different to distance. The way it's similar is obviously that, you're measuring a change in position between two objects, or between two places that the object is moved from and to. But with distance, you could change direction any number of times, and you could still calculate the total distance moved. Now, the difference here with displacement is that it is a change in position, but it's only one change in position, which is that it's the difference between the start and the end. So just to highlight a quick example, if I moved a few meters to the east, and then a few meters north, and then a few more meters east, and then a few meters south, and then several meters west, until I was just directly underneath my starting point. Displacement and distance would give you very different answers between the two. Displacement would actually only take you from the start to the end, which is the distance of that red line. Whereas distance would take you through each one of the steps, and it would calculate a running total of distance along the way. If you just compare those two lines side by side, this is just an estimate, but the blue line is going to be considerably longer. I'm guessing about that much longer. And this one, the red line, since it's a displacement, meaning just the distance from the origin to the final, displacement is vector. And it would have a direction associated with it. In this case, it was just a bit south of the starting point, but of course we'll have exact directions and exact measurements later on. And then over here, this one would be our example for distance. And it's a scalar quantity because it doesn't really matter the direction, it's just the running total of how much position has changed. All right, so just as for the record, distance and displacement are both usually measured in meters, but it could be centimeters or kilometers. And the following example in the next slide is going to illustrate the difference between distance and displacement. All right, so in this example, we're basically moving on the New York State Thruway from Buffalo to Albany and then to New York City. So the highway connects all those towns. And the distance traveled by the car is approximately 418 miles, or if we're going to be doing physics, we should probably express that in kilometers, so 673. The magnitude of the total displacement of the car, however, is only the length of the vector, or we could call that straight line, that connects Buffalo and New York City. Which is actually only 313 miles. So even though the car is going 418 miles total, the straight line that connects Buffalo to New York City is only 313 miles. So this is really highlighting the difference between distance and displacement, because the difference in the number of miles between 418 and 313 is because the longer distance is, or the larger number, which says 418 miles, it's larger because it's measuring the total distance, whereas the smaller number, 313, is actually just measuring the distance from the start to the end, so it always takes the shortest and the straightest path. So I just wrote in that 418 was a distance, whereas 313 was a displacement. So what you can do, this is an extra extension here. As it turns out, you can take two or more displacement vectors and you can combine them to obtain the vector sum. We would call that actually a resultant. So I think this is the first time you're seeing that word, but we call that a resultant when it's the vector sum. So in this problem, the student is going to walk 5 meters east and then 12 meters north, and we'll just calculate the magnitude and the direction of the resultant displacement. So one step at a time. If you start out here, and he goes 5 meters east, and then turns and goes 12 meters north, it's probably not to scale, this is just my best guess. Goes 12 meters north, and we want to know the magnitude and direction of the student's resultant displacement. Okay, so its displacement is just the position change from the origin until the final position. So the final position is sort of inside this circle here, and the initial position is at the black X. So if I draw a line from the start to the finish, then that red arrow is going to be the displacement. But the question asked me to solve for the magnitude as well as the direction of the displacement. Magnitude is going to be a little easier. I would recommend Pythagorean theorem for that. And then the direction would be a little bit harder. I'll have to use trigonometry to find that one. So I'm starting out by writing the Pythagorean theorem to help me with my magnitude part of this question. And I'm going to rearrange it right now so that it solves for C, because we're looking for the hypotenuse. So that wasn't too bad. I just took the square root of two sides. And now I'm going to plug in. I'm going to zoom in a bit to do that last little piece. And I would say that C is going to be the square root of 169. I guess square meters. And the square root of 169 is going to be 13. And the square root of meters is meters squared is going to be meters. So yeah, I got 13 meters as the magnitude, but I also need to get the direction, and that's going to be an angle. And the angle that I'm describing is, I'll do it in blue, is this angle. And that's going to make this side A and that side B, and that'll make that side C. And then we can just find the angle using really sine, cosine, or tangent. But since we did just solve for the hypotenuse, one thing that you could do is to use tangent, because tangent will use side A and side B, and it won't use side C. So to use side A and side B, and those were both given, so I know they're correct. I'm going to go ahead and write in the equation for tangent now. So it says tangent of theta is A over B, and we're looking for theta, so I'll just sort of leave it set up the way it is, but I'll need to do an inverse tangent in a moment. So tangent of theta is going to be side A over side B, and side A is 12 meters, whereas side B is 5 meters. And you're going to get a decimal if you just do 12 over 5. It'll be a whole number with a decimal. But you also need to do an inverse tangent. So there's different ways to do that on your calculators. But it'll often look something like that. It'll say tan to the -1. You might even see 1 over tangent as an option. So just find the inverse tangent of this ratio, and that'll be our theta. So in my calculator, I got 67.4, and that is with rounding. And so that's part of my final answer for the direction. But I just need to say 67.4 degrees what, because that could be really in any direction around the circle. But if this direction is east, and I think it is by definition, then and I move along this angle for 67 degrees, then I'm actually moving above east, right? So I'm starting out at east and moving above it. So that means I will be ending at 67 degrees north of east, so meaning a bit above east. So I'll write in 67.4 degrees north of east. So I have some tips and tricks for using these resultants for displacement. If their motion is all in a single straight line, you're in luck because you can do just algebra on it. So let's say that in the previous problem, instead of going 12 meters or 5 meters east and 12 meters north, let's say that the person went 12 meters east and 5 meters east, then the resultant just would have been 17 meters east. And then if the student had gone 12 meters west and then 5 meters east, you can really just subtract them, but visually you might want to know what's going on. So 12 meters west would be maybe something like that, and then 5 meters east, maybe something like that. So 12 west and 5 east. So you're really just going to be getting 7 meters west of the starting point, because the starting point was there, and there's the ending point. So your vector is going 7 meters to the west. All right, so when you have successive displacements that are not along the same straight line, however, then you need to use a graphical method for finding the displacement. So let's say that a person walks 5 meters due east, and then they turn. and they go 12 meters at 60 degrees north of east. So east is to the right. I'm going to just draw an angle that looks about like 60 degrees to me. So that to me looks about like 60 degrees, and it is north of east. So it's going to go along that line for 12 meters. And then in order to find the magnitude and direction of the person's resultant displacement, we would really just need to find out what this distance is, along a straight line, of course. And then it's generally moving in this direction, and the angle would be that one. And I think you would measure it north of east. So without laws of sines and cosines, which we don't use in this class, the best way to solve this is just by using a scaled drawing and also using a metric ruler and a protractor. So basically, if you can just decide that, for instance, 1 meter is equal to 1 centimeter, so every time it says 5 meters due east, then this line needs to be, let's say, 5 centimeters. And when it says 12 meters at 60 degrees north of east, then just make sure that that line is 12 centimeters long and that you measure the angle 60 very carefully. And then all you'll have to do to find your final answer is you'll just need to measure the distance from here to there. So from the start to the finish, and then you'll just convert it back into meters. So maybe you'll get, let's say, 18 or something centimeters. Then you would just say 18 meters, and then you'd measure this angle in this blue line right there, and that angle would be the direction. I would like to solve this one graphically in class. So please make a note of this one, put a big star beside it, and remind me in class that we should practice this graphical method together. So this slide just attempts to clarify any confusion that we may have had so far about speed versus velocity. So first of all, we base it on this equation. It says v bar equals d over t. So it's saying average velocity, or sometimes average speed, is distance over time. If d is distance measured in meters and t is time measured in seconds, then the unit for average speed has to be meters per second. I'll write that in. And just know that if that speed does not change over the course of time, if that speed remains constant, we would refer to that kind of motion as uniform motion. But if the speed does change and the object accelerates, then we would call that non-uniform motion. Velocity and speed are very similar. For instance, you could have two cars that one of them's going 88 kilometers an hour due east and the other one's going 88 kilometers an hour due north. Those cars actually have the same speed, because speed really is just the magnitude of an object's velocity. But they have different velocities overall. And they have different velocities overall because they have different directions of motion, and that really matters. Now, linear motion refers to an object's change of position along a straight line. And on a straight path, there are really only two possibilities for velocity, because there are only two possibilities for direction along a straight line. If you are doing all your velocities along a straight line, it's sometimes helpful just to think of something like to the left, for instance, as having a negative velocity, and to the right as having a positive velocity. It certainly simplifies your math if you do that. This slide just has some helpful tips and tricks for how to analyze some of the graphs that we're going to see on the next slide. Without going into too much detail, the first tip is that on the x-axis you're going to have time, on the y-axis you're going to have position. The slope of a position versus time graph is going to give you speed, and if that slope is positive, then think of it as a positive speed, and if the slope is negative, think of it as a negative speed. And then if you have a slope of 0 or a straight horizontal line, then that's going to indicate an object at rest, because, of course, the slope is 0 at that point. If you manage to get a position versus time graph that is curved, then you can draw a tangent to a curve at any point to find an instantaneous speed. And the instantaneous speed, or the instantaneous velocity, is the velocity of an object at any particular instant in time. So it's not by any means average, it's a particular instant of velocity. So here are 6 examples of position versus time graphs that bring up a little bit of each of the things I was just discussing. So in the first graph, first of all, the slope is positive, and the slope on this graph is position over time, which of course is speed. So if the slope is positive and the slope is speed, then the speed is positive. Also, the slope doesn't change, so it's has constant speed in the positive direction. In my next example, we are going to do basically the same graph, but it has a negative slope. So let's just say constant speed in the negative direction, and that's based on its negative slope. In the next graph, we have a 0 slope. So that's pretty easy. That means that there is 0 speed, or the object is at rest. In the next example, we have our first example of a non-uniform motion, meaning that it starts out at a velocity near 0, and I'm determining that by just drawing a very simple tangent to the curve at that point. And if I want to check the speed up here, for instance, I need to draw another tangent to that curve. And the slope is much higher in that second graph. So what I know for sure is that we have increasing speed. The speed is not constant. And we can do basically the reverse for the next graph. You can draw a tangent to the curve at some point at the top, draw another tangent to the curve down towards the bottom, and you can see that the slope is considerably closer to 0 in the red line, but throughout the entire trip it is negative. So what I would say is that we have decreasing speed because the slope is decreasing. And the last graph is sort of the doozy. It mixes pieces of all different kinds of these graphs. Firstly, it does say that between sections A and B, that the slope is constant and therefore the speed is constant. It's also positive there, so I would just say between A and B it's constant positive speed. Between B and C, you have a flattening of the slope towards the top. So I would say that speed is decreasing as the slope decreases towards the top. So constant positive speed, a reduction in speed, and then between C and D, the slope goes to 0 and the speed goes to 0, so it is motionless. So I would say constant positive speed, reduction in speed, no speed, motionless. Okay, so when we're talking about acceleration, I went ahead and I prepared some stuff that needs to be on this slide. I made a little graph I think that'll help. Just know that the equation for acceleration is the average speed over time, which means that its unit is going to be meters per second, or meters per second squared. And also, this is an equation that's not in your reference table. It's to help you find average speed if you ever need it. Just take the initial speed and add the final speed and divide by 2. It's sort of like the equation for finding the midpoint of a line, because if you think of this as a speed versus time graph, and you start at, let's say, speed 8 and end at, let's speed 28. This is sort of a preparation for a question there. But if we start at speed 8 and end at speed 28, assuming that the slope of the line is constant, meaning that the, in this case, acceleration is constant, then the midpoint of that line represents the average speed during travel. So we can use this equation to help us find that midpoint, basically. We would just take the initial speed, add it to the final speed, that's vi plus vf, and then divide by 2, and that would give you the midpoint. So in this case, it would be 8 plus 28 over 2, And I'm getting, I think, 36 over 2, which is going to be 18 meters per second would be the average speed for that guy. All right, so let's answer this final question. It says that a particle has a constant acceleration of 2 meters per second squared. Calculate the time required for the particle to accelerate from 8 to 28. So as it turns out, we've done part of the work already because we just need to use this equation that says that acceleration is average speed over time. And I just found the average speed. I'll circle it in red. It's 18 meters per second. So I know that variable. In the question, it says that the acceleration is 2 meters per second squared, so I know this variable, and I'm just going to try to isolate t. So that's what you're going to watch me do here. So I just rewrote it, and I circled t. So right now, t is being divided on the right-hand side of the equation, and one thing you can do at this point is just multiply both sides by t. And if you do that, you'll get a cancellation of t on the right-hand side. And your intermediate step will say that v bar is a t. And then we still want t alone, right? So I'm going to divide away an a on both sides. And then I'll find that t is v bar over a. So that's going to be the equation I use. And v bar, I found earlier, was 18 meters per second. And the acceleration is in the question. It says 2 meters per second squared. So my final answer is going to be 9 seconds. Here's a sample problem where we can put some of these skills to use. There's a reading up here. You should pause the video and read it now. But it's related to this graph to the right, which is a speed versus time graph. And that means that the slope is going to be acceleration. And my reasoning for that is, again, slope is rise over run. So the rise would be meters per second, and the run is seconds. So you're going to get meters per second over seconds. And I'm going to use that for part A of the question, which says calculate the magnitude of the child's acceleration. The easiest thing for me to do is just find a slope of that graph. So since this motion is uniform, it doesn't really matter which points on the line I choose, but I'm going to stay consistent, and I'm going to go with the ones that have already been plotted. So the rise for me is the difference between 10 and 4. So 10 and 4. And the run, in this case, is the difference between, it looks like 4 and 1. So 10 minus 4 is 6, 4 minus 1 is 3. So I'm getting an acceleration of 2 meters per second squared. And in the second part of the question, it says determine the average speed of the child. Remember what I had said earlier, that when you have this uniform motion, the average speed is going to be the same as the midpoint. The midpoint can be found by just basically taking the difference here and dividing it by 2. I guess you could do it either way, really. You could find the average time as well, but in this case we want the average speed, so we need to go on the y-axis where speed is. So B, I would just say average speed is going to be VI plus VF over 2, and VI is 4, and VF is 10, divided by 2. So I'm going to get 14 over 2 is 7 meters per second. And in the last question, it says calculate the total distance traveled by the child during this 3-second interval. I think that probably the best way to solve this one is to think of it graphically as just this interval, And it looks to me that the easiest thing to do is just to make a rectangle out of the bottom, and then you have a triangle at the top. So I'm going to put in my equations and then I'll come back. Okay, so I put in my equations for the area of a triangle and also the area of a rectangle. So the triangle is this guy up here. And the base of it is going from, it looks like 1 on the x-axis to 4 on the x-axis. So it has a base of 3. And it has a height of, looks like 4 on the y-axis and 10 on the y. So that height is 6. So after the calculation, I think that you'll find that it's going to be 9 meters as its displacement. And then for the next one, it's just a rectangle, but it's going to be a base of 3 and a height of 4. So that's going to give you a total displacement of 12 meters for that part. And then you sum those together, and I'm getting 21 meters of total displacement during the 3-second interval. So this slide is really just a primer in the skill that I just used to find the distance traveled by the object. It's just suggestions for solving for distance in a velocity versus time graph, which is just to be mindful that if you find the area, you're essentially doing base times height, or you're multiplying to get the area. And when you're multiplying on this graph, you're really multiplying a unit of meters per second on the y-axis by a unit of seconds on the x-axis. And when you do that, the seconds cancel. And that's why you get an answer that comes out in meters. So that's the basis of the logic. So multiply the axes and you will get an answer that comes out in meters, which is an answer to, like a displacement or a distance question. But do keep in mind that generally we're going to limit this to rectangles and triangles. And if it's a triangle, the equation is 1/2 BH, and for a rectangle, the equation is BH. Okay, so here are some of my tips for reading velocity versus time graphs. Since a velocity versus time graph has velocity on the y-axis and time on the x, then doing a slope is going to give you an acceleration because of this equation. And just know that if the slope is going in the positive direction, then the algebraic sign of the slope will tell you that the acceleration is positive. And if the slope is going in the negative direction, then that also means that the acceleration is negative, which is the way physicists refer to a speed slowing down, by the way. And then a horizontal line with 0 slope indicates constant speed. And this is a big, very important thing. Constant speed means 0 acceleration. That's something that people don't think about a lot. But if you're moving at constant speed, you can have all that speed as long as it's constant. That means your acceleration is very specifically 0. If you have a straight line with a positive slope, that means you have increasing speed or constant positive acceleration. Straight lines with negative slopes have decreasing speed and constant negative acceleration, which maybe you could say is deceleration, or you could just say the speed is slowing down. And then if you have a line that intersects the horizontal time axis, that indicates a change in direction. And I'll point that out on the next slide because that's kind of hard to understand. And then lastly, a curved velocity timeline indicates that acceleration is not constant or that speed is changing. So we'll just use this slide to talk about velocity versus time graphs, especially for vertical motion. So that's why I have this diagram here, but it's only going to apply to certain graphs. So firstly, graph A and B both have objects moving at constant velocity, but since A is farther from the x-axis than B is, then that means A is traveling faster. C and D are in a similar situation, except that C is in the positive region of the velocity graph, and then D is in the negative region. So that means that, I guess I would say that D is moving faster than C, but it is moving in the opposite direction because it's in the negative zone. So it's faster because it's farther from the axis, but since it's negative, that's what makes it go the opposite direction. Right here we have, this is called uniform acceleration because the speed is constantly increasing, speed on the y-axis, so the speed's increasing, so that's uniform acceleration. And this would be uniform deceleration, whereas the velocity is constantly decreasing over time. So is this one. This is also uniform deceleration up to a point anyway. So it looks like section G between 0.1 and 0.2 is what I'm talking about. You are going from a relatively large positive speed to a speed of 0. And that means that you're uniformly decelerating. But then it gets interesting, which is that it goes from a speed of 0 to a large speed. It's just going in the opposite direction. So this graph right here is a really great graph to study for quizzes and tests because it totally applies to this diagram right there. So basically, from 1 to 2, it's starting at a large speed, ending at a speed of 0. So this would be, I guess, 0.1. And then this would be 0.2. And then after 0.2, you're moving into 0.3. You are getting more and more speed, but it's going in the opposite direction. So this is 0.2 again, and then 0.3 is down here. So it's going just as much, it's gaining just as much speed, but it's going in the opposite direction. And in the last example, right here, it says h is at rest up to time 1. Okay, so we are having 0 velocity up until time 1, and then it looks like it is accelerating over time. And it's a non-uniform acceleration because it's not a flat slope, it's a curving slope. All right, so we're finally going to start using some of these kinematics equations on this slide. So we're going to find final velocity and distance traveled during constant acceleration. So acceleration is defined by this formula. A is delta v over t, and delta means change. So it's really, if A is delta v over t, then you're really just looking at this. A is vf minus vi over t. You can rearrange this so that it yields this equation. It says vf equals vi plus AT. And this one's on your reference table, VF equals VI plus AT. So it's saying that final velocity is the initial velocity if you add to it the acceleration and multiplied by the time. We can use that equation to solve this question right here. It says an object starts from rest and falls freely near Earth's surface for 3 seconds. Calculate the final speed of the object. All right, so the final speed is VF. So we don't even need to rearrange this equation. It's nice and set up for us. So you start out by just writing VF equals VI plus AT. And we already are solving for VF, so I can start plugging in. VI, or the initial speed. Now it says the object starts from rest, so the initial speed is 0 meters per second, and the acceleration near the Earth's surface is on your reference table. You'll find it on the front page, and it's 9.81 meters per second squared, and then the time that it falls is in the question, that it's going to be for 3 seconds only. So you multiply that stuff, and 3 times 9.81 is, I got a final speed of 29.43 meters per second. All right, so here are a couple more equations. I'm not going to use them right now on this slide, but they're both on your reference table. You'll find them nearby this equation. The first one that I'll introduce is d equals VIT plus 1/2 AT squared. So it's saying that the displacement that occurs during the travel is going to be equal to the initial speed multiplied by the time of travel, and you would add to that half of the product between the acceleration and the time squared. And then the next one says that VF squared equals VI squared plus 2AD, and it's saying that the square of the final speed is equal to the square of the initial speed if you add the double the acceleration and the product of acceleration and distance. So I'm going to solve all three of these sample questions for you. And one of the first things that you need to do when you're solving these is to choose the equation that fits the question. So what I'm going to do is I'm going to quickly help you choose those equations first, and then we'll come back and actually do the algebra and plug in and solve. So the first one, it says starting from rest, that's a speed, by the way. So VI is 0. An object rolls freely down a 10-meter long incline in 2 seconds. What is the acceleration of the object? So I'm going to label some stuff that I see. The first one is starting from rest. It's saying that VI equals 0. An object rolls freely down a 10-meter long incline. So this is a distance. And it takes it 2 seconds. That's a time. What's the acceleration? So obviously that's A. So we have a VI, a D, a T, and an A. An equation that would match that pretty well is on your reference table. I want you to take a moment and pause the video and choose an equation that matches those variables. So the equation I chose is D equals VIT plus 1/2 AT squared because each of the variables in that equation are ones that are available to us in the question. So as I said, I want to go through and choose the right equations first. So let's go to the next question. An object initially traveling at 20 meters per second, that's a VI, accelerates uniformly at 4 meters per second, so that's an acceleration, 4 meters per second squared. East for 2 seconds, that's a time. What is the displacement? That's D of the object during these 2 seconds. That's still time. So we have a VI, an A T, and a D. So take a moment, look at your reference table, and choose an equation that matches those variables. I'm seeing again that a good equation is D equals VIT plus 1/2 AT squared. All right, last question. A car is originally traveling at 15 meters per second. The driver applies the brakes. Let me go back and label this. So it's traveling at 15 meters per second, so VI. The driver applies the brakes, causing the car to decelerate uniformly at 4 meters per second squared. So that's A, until it comes to rest. So if it comes to rest, then that means that that's a VF, because it's saying that the final speed is 0. Calculate the car's stopping distance, so they want to know D. So I have available to me VI, A, VF, and D. So choose an equation that matches those variables. So I found an equation on my reference table. It says that VF squared equals VI squared plus 2AD, and that's all the variables that we have. All right, so now we're going to go back to the first question, and we're going to rearrange it so that it solves for what we're looking for, which is, in this case, acceleration. So the first thing that I would point out is that VI is 0. So that means that if I put a 0 into this section, it's going to multiply it by t, but it'll drop out because the VI is 0. And my new equation would just read something like this. D equals 1/2 AT squared. But we are still looking to solve for A. So what I'm going to do is I'm going to divide both sides by 1/2 t squared. And when that happens, I'll get a new version of the equation that would say that A equals D over 1/2 t squared. So this is the point where I can start putting in variables. So instead of D, I will say 10 meters. And there's the fraction 1/2. And then instead of t, I'll say 2 seconds. So it's 2 seconds, but it is squared, so make sure you square that. And I'm getting between the 2 and the square is a 4, so half of 4 is 2, and then 10 over 2 is 5. So my answer is 5. This is an acceleration, so meters per second squared. All right, so next question. We are looking for the displacement. So it's that. We don't need to rearrange it. I'll just start plugging in variables. So let's see, VI is 20 meters per second, and T is 2 seconds. And we're going to add to that the quantity, 1/2 A. A is in the question stated as 4 meters per second squared. And then we have T squared. And T was 2, but it's going to be squared. So I'm going to start combining that stuff. So I'm going to get, I think, 40 meters on the left. And on the right, we have 2 squared. So that's 4 times another 4 is 16, and then half of that is 8. So 8 meters, and that means that my final answer is going to be 48 meters. All right, last question. A car is originally traveling at 15 meters per second. The driver applies the brakes, causing the car to decelerate uniformly at 4 meters per second squared until it comes to rest. Calculate the car's stopping distance. All right, so we're looking for D in this equation. And let's see, we're just going to rearrange it. I mean, from here, it's not a big deal. So you just subtract VI squared from both sides, and then you get VF squared minus VI squared equals 2AD. Still looking for D. And we're going to divide both sides by 2A now. On the right-hand side, it cancels the 2A. And that means that D is VF squared minus VI squared over 2A. So I'll plug in variables. And VF squared is going to be, well, 0 squared. So I'll just write 0. VI was 15, so I'll write 15 meters per second squared. And then the acceleration was 4. So on the bottom, we'll just have 2 by 4 meters per second squared on the bottom. So I'll get some final calculations now. It says on the top that we're going to be getting like negative, I believe 15 squared is 225. So negative 225, meters squared per second squared. Over, I'm getting 8 meters per second squared. After all that stuff cancels, you are going to get a final answer that's just meters or distance. And 225 over 8, give me a second. I got an answer of 28.125 meters. So with sig figs, I think that I only get to keep 3 digits. So I'll write 28.1 meters. Okay, this is our last slide of material. You guys have been amazing. Let's just get through this last slide. So it says, in a vacuum, in a space where there's no matter, a coin and a feather would fall at the same rate. Now this might be contrary to what you would believe, how you believe a coin and a feather would fall, but they're both being acted upon by the same force, which is called gravity, and they're both going to be going through the same kind of motion, and that motion is referred to as free fall, because there's predominantly only one force acting on that feather and acting on that penny, and that's gravity. And then fun fact is that gravity is 9.81 meters per second squared on at least planet Earth near the Earth's surface. So you've noticed that when you do drop that penny and when you do drop that feather, that the acceleration of the feather is actually much less than that of the coin, or the coin moves faster. So the reason for that is because of air resistance, which is that They both have relatively light masses, but the penny is much more streamlined and the feather has a lot more aerodynamic drag involved with it. So it's going to have a much lower acceleration. Over time, it's going to fall a lot slower. Now I put in a data table that just highlights some of the really important facets of speed and distance traveled when an object is in free fall. So in the first question, I'd just like you to pause the video and think about what's happening to the speed each second. So just notice that the seconds are going up by 1 for every row, and what's happening to the speed every time you move just through 1 second. So pause the video and think about what happens every time you move through 1 second, and just notice something. So one thing that a lot of people notice is that it seems like every second is giving you an extra 9.81 for the speed, meaning you're starting at 0 and then you have a 9.81, and then if you add another 9.81, you get 19.6. If you add 9.81 again, you get 29.4. If you add 9.81 again, you'll get 39.2, and if you add 9.81 again, you'll get 49.1. So the reason for that actually lies in the definition of acceleration. The acceleration is called the time rate of change of speed, which is meaning it's the rate at which speed changes. And if acceleration is constant at 9.81 meters per second squared, then what that really means is that every second you're increasing by 9.81 meters per second. That's why we say meters per second squared, because it really means meters per second, which means how many meters per second or how much speed you're changing every second, and that's meters per second. So you're adding 9.81 each time. And in the second part of this question, I want you to consider what happens to the distance traveled after every second. So pause the video and see what you notice as that happens to distance. So one thing that a lot of people notice for that is that you start out with a modest gain in distance, but it quickly goes up to, almost 15. So it maybe starts with about 5, and then 15, then 25, and then maybe 30, and then followed by, all like 43 or so in that last bit. So the amount of distance covered each second is increasing at every 1 second interval. And the reason for that is that, well, to be quite frank, the speed is increasing every time. So if you're moving at this speed for 1 second, you're going to cover this much distance. You'll cover 49.1. And if you're moving at, let's say, this speed for a second, then you'll cover that much distance, or about 30. So the faster the speed is during that 1 second of travel, the more distance will actually be covered. So I went ahead and gave you a printout of this pair up. Do not write any of these down. You have a printout of them. We'll solve them in class when I see you guys next. And you should have this summary as well. So again, don't do anything with it. Just keep it, and we'll put it into classwork, and we'll work on it as classwork when I see you guys next.